In this video I'm going to be talking about the convergence of indirect methods. So indirect methods for solving linear systems of equations, this is where we have an estimate for our solution and we iterate some iterative scheme until two estimates of a solution hopefully converge. Now that's not always going to be the case, and there is a way of determining whether methods will converge, and they will converge if rho t, and I'll explain what rho t is in a minute, is less than or equal to 1. Okay, so methods will converge if rho t is less than or equal to 1. So rho t is the largest absolute value or absolute eigenvalue of a matrix T, and T is what we call an iteration matrix. So T is known as an iteration matrix, okay, and what do I mean by that? Well, if we have some solution, or we're updating our estimate of our solution, so we have x is our vector terms for which we're trying to solve, okay, and what we do is we do something to x, or our current solution. Okay, so whatever we do to our current solution to achieve our improved solution is our iteration matrix, and we also have some constant vector c. So an example of an iteration matrix, if I take the Jacobi method for an example. So for Jacobi, if we looked at the matrix form of the method, okay, so in an earlier video I showed this matrix form. Okay, so we have L plus U times the current solution for x. Okay, so that's a matrix form. Now remember, D was the diagonal elements of the coefficient matrix A. So this is what we're trying to solve. So A is our coefficient matrix, D are the diagonal elements of A, L are the lower triangular elements of A, and U are the upper triangular elements of A. Now if I rearrange this slightly, what you'll see, so what I'm going to do is rearrange this slightly, so I'm going to split up these two terms in the bracket. So I'll have minus D inverse, so minus 1 times D inverse, that's times L plus U, and that's multiplied by our current solution x. So notice what I've done here is I'm separating this from the constant vector b, and we'll also have d times d inverse times b. Now this here, this is just some vector. Okay, it's just going to have some numbers. This is the part I'm interested in. So this part here, which we're multiplying by x, that is our t. Okay, so for the Jacobi method, I'm going to say t and t subscript j for Jacobi. Our iteration matrix is minus D inverse multiplied by L plus U, and remember D, L and U all come from that coefficient vector A. We could do similar for the Gauss-Seidel method. So if I use T subscript GS for Gauss-Seidel, so for the Gauss-Seidel method we could do similar, and we get L plus D inverse times U, and you can see where this comes from. I think I've given an example in the lecture notes. Okay, so what we do is when we're presented with a linear system, we calculate the iteration matrix for the method which we want to use, calculate the eigenvalues of the iteration matrix, and look at the largest absolute eigenvalue of t. So if you've got imaginary values, remember you have to take the modulus. So the largest absolute eigenvalue of t, if that's greater than 1, it does not converge. So that has to be less than 1. Furthermore, the smaller the value that rho t is, the quicker your method will converge for that system. So let's have a look at an example. and this is similar to an example we've looked at previously in the previous videos on indirect method. So we had a coefficient matrix, a 3 by 3, 2 1 1, 1 3 2, 1 minus 2 4. Okay, so for this, our diagonal elements, if we just take the diagonal elements, is going to be the matrix all zeros apart from the diagonal elements of A. Our lower triangular elements will be all zeros apart from the lower triangular ones, and similar for the upper triangular. So 0 1 1, 0 0 2, 0 0 4. Okay, so for the Jacobi method, we have minus d inverse L plus u this is our iteration matrix. So we have minus, now the inverse of a diagonal matrix is just the reciprocal of the main diagonal elements, so 1 over 2, 1 over 3 and 1 over 4, and that's multiplied by L plus u, and that's quite easy to see. All it is A, with the main diagonal elements being 0. That's going to be 0. Okay, if you multiply those two together, we get 0 minus a half, minus a half, 1/3, 0 minus 2/3, minus a quarter, a half, and 0. Okay, so now I need to calculate the eigenvalues of Tj. Now it's a 3 by 3, so I could do it by hand, but I'm going to sort of cheat and bring in MATLAB to help me. Okay, so here we have this is the same coefficient matrix as I've got here, and it's just simply one. First thing I have to do is calculate the iteration matrix. So to do so, I need the lower elements of A. Now there's a little trick here. Try L give us a lower triangular part of a matrix. So if I was to do try LA and run that, you notice it's also included the main diagonal elements. So what I can do is I can say start from the -1 diagonal, which is this diagonal here. So if I show you what that does, you can see it only includes the lower triangular part. So that's L. D is similar, but for try then U, and if I did the same, try UA is also included the main diagonal elements. So what I can do is I can say start from the diagonal above. Okay, so you can see that's not included the main diagonal. Oh, that's meant to be U, not D, and the main diagonal elements, well, what we can do is we can just subtract L and U from A. So you see. Okay, so I've got L, D, L, U and D. Okay, so what I'm going to do now is calculate this iteration matrix. So that's Tj, this is minus the inverse of D times L plus U. And that's given me that matrix there. Okay, so all that remains is we calculate what's called the spectral radius of Tj, and that's so I'm going to call it rho T. J is equal to the maximum absolute and eig, which is the eigenvalue command of Tj. Right, so I've done that, and rho Tj, so the spectral radius is 0.7003. Okay, so we've done that calculation. So rho of Tj is equal to, it was 0.7 something. That is less than 1, so therefore the Jacobi method will converge for this system. Okay, we can actually do the same for the Gauss-Seidel method. So just out of interest, let's go back to MATLAB. Okay, so here we calculated Tj. I can calculate I call it TGS. So this is the this is the iteration matrix of the Gauss-Seidel method, and that is the inverse of L plus D multiplied by U. Okay, so this is the iteration matrix for the Gauss-Seidel method. So again, if I say rho TGS is equal to max abs ig TGS, and you can see we have 0.2887. So if I can write that here, so if we do the same for, oh, I've got that wrong again. We do the same for the Gauss-Seidel method, and I've forgotten it already. 0.2887. So this is also less than 1, which is good news. So our Gauss-Seidel method will converge, but notice that the spectral radius of the iteration matrix for the Gauss-Seidel method is much less than for the Jacobi method. So that means the Gauss-Seidel method will converge, but also much faster than the Jacobi method.